So these questions are going to be done throughout this video, and it is according to the number of the questions over here. So 1, 2, and 3, and 4. That's a part of the timestamps. It's going to be example 1, 2, 3, and 4. So just pay attention to the timestamps on the progress bar on the video, and whichever one intrigues you the most, you can go to it immediately. Okay. So this is going to be improper integrals. Let's get straight into the introduction. Okay. So let's first start off with the following, right? Well, we know with integration, definite integration, right? We're going to have over here, let's say a graph. And I'm going to do two sets of axes like this. And then let's say that we have a graph that looks something like, let's use a very common graph, right? Where we have something like this. Okay, that's not the most symmetrical one, but it normally looks something like this. And then there we go. So it's symmetrical on both sides, meaning that, yeah, it's very straightforward. It's symmetrical, meaning that if you find the area on this side of the x-axis, like the positive side, then that is just basically going to be the same as this on this side over here, the area on that side. Okay, that's what I mean by symmetrical. So what I'm trying to get to, right, is if we are trying to find, like, let's say from let's say negative infinity, I'm going to use red for this. Let's say it's from negative infinity until positive infinity. Meaning if we want to find the integral where we have it from positive infinity to negative infinity, maybe we would assume that it would be infinity, right? We would assume, oh, just because it's going from negative infinity to positive infinity, the area under the graph has to be infinity. Well, that's not always the case. And this is why we're going to go to improper integrals, because this is where we are going to be tackling convergence and divergence. Okay, so let's get straight into the introduction for that one. Let's just recap over it because I'm pretty sure you've learned it in high school already. Alright, so let's differentiate between convergence and divergence. Now, if we have some convergence going on, well, in our cases, when we assumed that if we had from positive infinity to negative infinity, we would assume that the outcome would be infinity, right? The area would have been infinity. Let's say of a function with respect to x would be equal to infinity, right? That integral. Or the area under the graph. How about that? But that's not always the case, because sometimes these functions can converge such that it won't really go to infinity. It will actually just, it will stay as a definite answer. That's basically what it is. So a convergence is essentially just not. So we can basically say it's not infinity. I know this is a stupid way of teaching it, but hey, it works. Convergence is when it's not infinity. And divergence is basically the opposite. It is infinity. And then when we do examples, I know it's not the best way to just teach it right now, but when we do the examples, you'll see. Because at the end of every example, I'm gonna say whether it's convergent or when it's divergent. And then you'll see the pattern that we follow. Okay, so just if you guys really want to know, convergence meaning the answer of the integral or the area under the graph is a definite answer, meaning any number, let's say for any number like 10 or 2 or whatever, like literally any definite answer. And then obviously divergence is like infinity, basically. Okay. And then there's one more thing that we need to take into consideration. Whenever we are dealing with these with this definite integral, I mean, is it a definite integral? Well, let's just look at this, right? If we have, let's say, for example, the integral infinity, and we have a, right? I'm not going to think about a number right now. We have a. Then, therefore, well, we can't really just plug it in as infinity because infinity is not a number. But what we do remember is limits. Oh, crap. We are back to limits. So let's say of a function with respect to x, we can also write this as the limit as we need to set a variable, right? We know this is both going to be x, but let's just set the infinity to let's just set a certain variable to approach infinity, and the most common variable that is used is t. So t must approach infinity in our case. And what is going to change? Well, we're going to have the integral. So it's basically multiplying by the integral. And then we're going to actually replace the infinity with t. Okay. Now note that these, if you can remember, these are actually limits. Remember, this is an upper limit. I'm going to say is UL. Well, upper limit. No, I'm not going to do it like that. It's the upper limit, right? And then this is going to be the lower limit. If you can remember from my explanations, if you watch my explanations or any other explanations from other YouTubers. And then let me just finish this integral here so it can look right. Okay, so that's what it would actually look like. We are just taking this infinity out so that we can actually make some variable approach at infinity, because we know infinity is not a number, and infinity is not definite, it's indefinite. Okay, cool. Now let's actually go straight to an example, or we're going to do the 4 examples, and then you'll see how the pattern goes. It's actually not that bad at all. It's just one extra step, which is the limits and conversions and diversions. You know, I don't even know if you guys ever even notice about this title over here, or this heading on the top of the screen. I actually forgot to change it from definitive integration to improper integrals. But you know what? It really doesn't matter. As long as you guys are consuming this information, then I'm happy. Instead of trying to shout at me for not changing these headings. Sometimes I have these weird Easter egg headings that maybe you wouldn't even notice. So sometime, maybe through the video, be aware of this heading, and then maybe it'll be something funny, or maybe something like a reference. But yeah, let's not focus on that. Let's focus on the mathematics, the best part about everything. Okay, so what we have is an improper integral. Well, let's look at this first, right? We have infinity, okay? And over here, if you remember from the introduction, what we're going to do is we're going to take this infinity and make some variable approach it, okay? So what we are going to do, we're going to say equals to, and we're going to say the limit as t. We're going to use t approaches positive infinity. And this is going to be multiplying by the integral from 1 to t. Okay. And then this is going to be 1 over x with respect to x. Great. Now what are we having over here? Well, now we have this variable. Okay. I'm going to show you why this is actually important and why we actually do this. If you don't do this limit, and some of the YouTubers, I think I saw some of their videos, and apparently some of them, maybe they didn't even take the limit out. That is actually going to cost you marks. I don't recommend not putting it in, because markers are strict in university, especially college. So that's why I recommend just keep the limit. Okay. So now what we're going to do, well, what do we know? We can just straight up integrate this over here. Okay. So over here we still have the limit outside as t approaches infinity multiplied by, now we have the bracket over here, we're going to put it in parentheses. We know that the integral of 1 over x with respect to x is just natural log of absolute value of x. And we're evaluating from 1 to t. Okay. Now over here, what we have to do is we need to evaluate the stuff. We need to take the t in first, and then we have to minus it by what we take the 1 in for. Okay, so it's going to look like this. It's going to be t approaching infinity, and then bracket, and then it's going to be the natural log of, it's going to be t first. Remember, it's first the upper limit, and then it's going to be minus the natural log with the lower limit. Okay, and then over here, well, we have the following. Let's just look in this bracket quickly. What do we know about natural log of 1? The natural log of 1 is just equal to 0. So we don't have to focus on that right now. So therefore, we have the limit as t approaches infinity of the natural log of absolute value of t. Okay. And then from here, well, it's pretty much obvious what we can do. If you didn't know, you can actually take the limit straight into this natural log of t, and you can just write it as the natural log of the limit as t approaches infinity of t, but we're not going to do that over here because I'm pretty sure we know how to do that already. That's only when you're learning it for the first time, then you would just get used to that. But now we are in calculus 2 now. Okay, we should know this stuff by now. So we're going to take this limit into the t, because you can see t is approaching infinity, and then therefore it will look like this, the natural log of infinity. And what is the natural log of infinity? Well, this is just going to give us infinity. So what are we going to say about this one? Well, for this one, if you can remember from the beginning, we want to determine if it's convergent or if it's divergent. And what do we say about divergent and convergent? Well, convergent is basically a definite answer, like a number, right? But divergent, or sorry, did I say? Hey, divergent is when it's infinity, and we can clearly see that it's infinity. So therefore, the answer, this was an arrow, is divergent. So that's the answer for the first one over here. Okay. Alrighty, we got number 2 in the house. Hell yeah. Okay, so what we are going to be doing, right? Well, I mean, it's pretty obvious what we're going to be doing, right? We are going to look at this integrand, right? Well, let's actually look at this infinity first, right? We can actually make a limit, right? Like we've just done with the previous example, we can do the exact same thing because you don't want that infinity to be on the top. So therefore, we're going to do the limit as t approaches infinity, right? It's going to be multiplied by the integral of, it's going to be 1 to t, right? It's like that. Now, what I'm going to do is actually the following. The only main thing that we can really do at this moment is integration by parts. And how so? Well, we can write this integrand as the natural log of x multiplied by 1 over x squared. Okay, with respect to x. Okay. And yeah, let's just do that, right? We need to do integration by parts, so we're going to do it in the following format. We need to have it into the integral of u with respect to v, which this will make it equal to u multiplied by v minus the integral of v with respect to u. Okay, so we need to get it into this form, which we already just did right now. This will represent our u. We're going to let this represent our u, and we're going to let this represent our dv. Okay. So let's let u be equal to the natural log of x, and then we know that the derivative of the natural log of x is just going to be equal to 1 over x with respect to x. Okay, we have that now. Now we need to find dv. Well, we know that dv, we let it equal to 1 over x squared with respect to x, right? Well, we can write 1 over x squared as x to the power of -2, so that we can just integrate. So now we're going to integrate both sides so that we can convert this dv into v. And then this is equal to, well, it's going to be x to the power of -2. And remember, we're integrating, so it's plus 1. And what is -2 plus 1? That's just equal to -1. Therefore, the denominator will also be -1. And this is, not with respect to x. So then, therefore, if we just write it a little bit more simple, we can write it as -1 over x. Okay. Easy as this. Okay. I'm not going to say pi because we haven't gotten to that yet. So over here, well, we can now write it like this, right? Well, remember, we're only working with this integral as well. We're not going to be focusing on the limit right now. We're only focusing on the integral, okay? And what I'm going to do is I'm actually going to just move this a little bit to the side so that we can actually have more space, because I don't like this space stuff. Okay, so now because we got it into the integration by parts method way over here, we're still going to have the limit as t approaches infinity outside, but remember, this bracket represents this integral. So therefore, we're going to say it's u times v. U, we know over here, is natural log of x. And then we're going to multiply it by our dv. No, not dv, it's v, sorry, which is -1 over x. So it's -1 over x. Okay. Minus the integral of v with respect to u. So we know it's going to be v, which is -1 over x with respect to u. And we know that du is equal to 1 over x with respect to x. Hey, would you look at that? But there's something incorrect about this. And I'm pretty sure most of you have picked it up already. Well, you are correct if you actually said that we are actually dealing with a definite integral. Well, I mean, you could say definite integral. But yeah, we have numbers, or I mean, a number and a letter. But we need to have it with respect to this definite integral that we are working with. So therefore, remember where these go. So I'm going to quickly move this to the side so we have a little bit more space, and I'm going to show you what we need to add, right? Remember that we also need to deal with, so we're going to take this whole thing. It was actually in the form of, let me just write it down here instead. So actually, if we were to talk about the integral from a to b, like this, right? Then therefore, it would have been the bracket over here, u times v, and it would have been a to b, minus the integral from a to b of v with respect to u. It would look like that. So that's where our numbers must go. So our numbers must go here. So it's going to be 1, and it's going to be t over here. And then over here, in the integral, it's going to be 1, and it's going to be t. There we go. Now we have dealt with it. Okay, so please do not forget about these, which you have to evaluate with, because that's the whole point of our improper integrals. Okay. All right. So from here, what we can do, we can actually just clean things up, right? Because it looks a little bit messy with all the negatives all around and whatever. So right, we have like a lot of negatives. So first of all, well, we can literally just write this whole bracket inside over there. So we know this is going to still be a bracket, but the inside bracket here, we can write this as negative natural log of x over x. And this is evaluated from 1 to t. Minus, well, I mean, yeah, we need to take out the negative quickly over here. And then a negative and a negative gives us positive. So this is going to be plus. Also, yeah, this is going to be plus, and this is going to be the integral from 1 to t. This is going to be 1 over x squared, okay, with respect to x, because we're just multiplying these x's together in the fraction. And then there we go. Also, I just realized that it looks like this, so let me do this quickly. There we go. That looks better. So now we can actually integrate this inside over here. So let's just deal with that quickly. So it's the limit as t approaches infinity. And what I actually want to do quickly is I want to take the limit into both of them to make things easier for ourselves. So I'm going to take the limit into this, and I'm also going to take the limit into that second term. So we have the limit as t approaches infinity of, and we're going to have negative natural log of x. We're not going to evaluate yet. I'm just going to quickly clean things up, and then it's going to be evaluated from 1 to t. And then over here, it's going to be plus the limit as t approaches infinity of the integral from 1 to t of 1 over, well, I mean, let's write it as x to the power of negative 2, because we're going to start integrating now. Okay. Now it looks like this. This is great. Now we can actually integrate this thing over here. Okay. So this is going to be equal to the limit as t approaches infinity, and then this is going to be of negative natural log of x over x, 1 to t. This is going to be plus the limit as t approaches infinity, like that. And now we're going to integrate. It took a while. And then we're going to put our brackets here. And what we know over here is that, wait, didn't we already integrate that? Yeah, we did. The integral of x to the power of negative 2 is already done over here, right? It's already done over here. So we know that the answer is going to be negative 1 over x. Okay. So negative 1 over x is going to be the answer inside of this bracket. But what I want to do quickly is I actually just want to take this negative outside of the bracket, which I can do. Okay. So I'm actually going to say this negative multiplied by this positive will give us a negative. So it's going to look like that. So it's going to be 1 over x. And this is evaluated from 1 to t. Okay. Great. Now, this is my one mistake that I've just made right now. I took the limit in, right? But I feel like that's a good thing, because some people actually prefer to take the limit in, or they would prefer to do it like this, right? They would rather prefer to do it by saying, let's say the limit, we're going to take the limit back out, by the way, as t approaches infinity, and then we're going to do this, right? Because the reason why I'm going to put them all in 1, and then I'm obviously going to take this limit out, is because, well, we have them both evaluating at the same range. So therefore, we can actually just include this and this in the same parentheses, or the same bracket. So therefore, it's going to be negative natural log of x over x minus 1 over x. Estimated or evaluated from 1 to t. Okay, because we took the limits. Or, you know what, it'll probably be better if we take out the negatives as well as a common factor. Wouldn't that be better? So if we take out the negatives as a common factor, well, all of them will be positive, but the negative will be outside. So this is what it's going to look like, right? So it's all going to be positive. So this is how it's going to actually look right now. So we're going to put that there, and we have the negative outside. I'm just making it easier to deal with. Okay. Great. Great stuff. So now, from here, we can just evaluate. Okay, so we have negative limit as t approaches infinity, and we're going to have the bracket here. And then this is just going to be, well, we're going to first deal with the t. Okay, so I'm going to do the t in red, and then I'm going to do the 1 in blue. Okay, so let's do the t. We're going to have the natural log of t divided by t, and this is going to be plus 1 over t, right? So we're just evaluating with t. And then this is going to be minus, sorry, because we are minusing them. And this is going to be the blue, which is going to be the natural log of 1 over 1 plus 1 over 1. Okay, and there we go. We have done the evaluation process now. And then over here, we're just going to continue. It's going to be the limit as t approaches infinity. And then we're going to have, now over here, right, we're just going to leave it like this for now. Okay. You're going to have the natural log of t. Well, let me just keep it in red for now. The natural log of t over t plus 1 over t. And then this is going to be minus. Now let's deal with this part over here, right? This natural log of 1 is just equal to 0, right? And therefore, 0 divided by 1 is just going to be equal to 0. Okay. And then 1 over 1 is just equal to 1. So this is basically negative 0 plus 1, which we can just write this as minus 1. Okay. Can you see how easier we made the blue side now? So now what we can do from here is we can actually just take the limit in from here. You see, I tried to get the limit away from everything so that we can clean up inside and then make it easier for us to evaluate. So this is going to be the limit, so negative limit as t approaches infinity of natural log of t over t. Okay, this is plus, it's going to, or actually it's going to be negative, because remember we're taking a negative limit, so therefore the plus, the signs will just become opposite. So this plus is going to flip to a negative. It's going to be limit as t approaches infinity, and then we're going to have of 1 over t. Okay, and then this negative sign is going to flip. But what do we know about the limit and a constant? This is just a constant, so it doesn't really affect the constant. So therefore what we're going to say is, well, it's just going to be plus 1. Okay, because remember we're also taking the negative in. So this negative one and negative will become a positive, represented here. Okay, so from here, what we're going to do is we are going to take this limit in over here. Okay, so let's deal with the easy part first. So I'm going to keep this like this, over t minus. Now over here, let's just go back to some basic limits over here. We know that the limit as x approaches any value, let's say over there, of 1 over x to the power of n, right? Where n is a positive integer. Like, let's say when n is an element of a positive integer, right? That's what we are trying to say over here. Then therefore, what we can say over here is that this value will be equal to 0. Okay. So that's what we need to remember. That's one of our theorems that we need to remember, or our definitions. So then because of that, right, we can clearly see, oh no, sorry, it wasn't A. Ah, damn it. Infinity. Only when it's infinity. Only when it's infinity. I don't know why I'm... Hey, anyway, it's hot. Really, really hot here. So basically what we are saying over here is if we take the limit into this, because t has a positive integer of 1, therefore this answer will just be equal to 0. And this is plus 1. Okay. And then therefore what we are left with is it's going to be negative limit as t approaches infinity of the natural log of t over t. And this is going to be plus 1 because we don't count this 0. We're just going to cancel it. Okay, and now let's deal with this last limit. We can clean up here. So let's focus on this part for now, okay? The limit as t approaches infinity of natural log of t over t. Okay, So obviously what we're going to have over here, if we do the direct substitution, so I'm going to do it over here in red, t approaches infinity of the natural log of t over t. If we do a direct substitution, then therefore it'll be natural log of infinity over infinity, which it would be an indeterminate form, right? It would be infinity over infinity. And if you're saying, oh, Dylan, but what if you write it like this? What if you write it as the natural log of infinity multiplied by 1 over t, where t is has a positive integer exponent. And therefore it'll be infinity multiplied by 0. Oh, crap. Guess what? Another indeterminate form. Now, what do you remember about Calculus 1, where we get rid of these indeterminate forms? Well, clearly we have a division, right? Over here between functions, and we must remember L'Hopital's rule. So L'Hopital. L'Hopital's rule is where you take the fractions, or a fraction or quotient of a function being affected by a limit, and then you just take that numerator and then you find the first derivative, right? And then you also take the denominator and you find the first derivative of that. Meaning we're going to take the derivative of natural log of t, and we're going to take the derivative of t. Okay. So what's going to happen if we do that? Now, what is the derivative of natural log of t with respect to t? That's just equal to 1 over t, right? And then this is divided by the, what's the derivative of t? The derivative of t with respect to t is just equal to 1. And therefore, we'll just get an answer of 1 over t. Whoa, that's crazy. And that's exactly what we're going to say over here. Okay. Also, sorry, I should have actually added the limit over here. It was remember, you still have the limit. The limit doesn't fall away when you're dealing with L'Hopital. Okay. Now it looks like that, and there we go. So that's what we're going to do over here. Okay. So that's indicated here. We have negative limit as t approaches infinity of, then we basically just did L'Hopital's rule. It's going to be 1 divided by t, or let's just write it as 1 over t now, okay? Because we've already just done it right now. Plus 1. And what do you note over here? This will be equal to 0. Okay, so therefore it's negative 0 plus 1, which is just going to be equal to positive 1. And now to conclude over here, is this convergent or divergent? Because it's a numerical value, because it's definite or definitive, it is converging or convergent. Let's move on to the next example. Okay, I know that was a very long example for the second question, but don't worry, this one will actually be a little bit of a break from it. But here's something different. Whoa, what is happening over here? What is going on? There's no infinity. Is this really an improper integral? Well, actually, yes, it is. You want to know why? Let's just pay attention to this function over here, right? Well, this function would actually look something like this. I remember I checked out this function on the function app, or Desmos as well, just to make sure. And it basically looks something like this. If we were only to focus on where x is equal to 0, so x is greater than 0, we would actually see a function like this, right? Well, we're going to have an asymptote. Remember, this is an asymptote function. We have an asymptote where x is equal to positive 3. Because if we have x equals to positive 3, then therefore we have x root 3 minus 3, which is equal to root 0, which is equal to 0. And then we're going to have 0 as the denominator, and that's undefined. So that means we have an asymptote. Let's put the asymptote here of positive 3. And then our function would look something like this. So basically it looks something like that. And what we are trying to determine is basically, let's just add maybe another number. Let's say 6 is here, right? And it goes to this point here. What we are trying to find is from 3 to 6, the area under this graph. This would be the function over here that we are trying to find, which is represented in the integrand. Okay, so that's what we're actually trying to determine. But obviously we can't use the point 3, right? Because it's an asymptote. Now what are we going to be doing? Well, because of the aid of this function, right, we know we have to take a limit. And we know that limits are not talking about what's exactly at that point. It's talking about around that point, either from the left-hand side or the right-hand side of that point. It's basically in close proximity of that point, which is 3 in our case over here, because it's a vertical asymptote, isn't it? It's a vertical asymptote of x equals to positive 3. That's the vertical asymptote, basically represented here. And now if we wanted to write this down, we would say the limit as x approaches 3 from which side now? Okay, we can't just say 3. We have to say one side, remember? Now the only way we can determine this is from what is the minimum? Well, we know that the minimum is actually 3 from what we have, and the maximum is 6. That's where we're trying to find the area for. And we're not trying to find anywhere from the left-hand side of 3. We're only trying to find from the right-hand side of 3. Therefore, it's going to be the limit as x approaches 3. No, it's not going to be x, by the way. It's t approaches 3, but from the right-hand side. Can you see why we have to pick left-hand side or right-hand side? We need to be familiar with our boundary, with our integral, with our limits of the integral. And then therefore we're going to have 6 over here, but we're going to have t at the bottom, because that's what we're replacing with the limit. So that was a little bit of an interesting one. I thought we were going to take a break, but unfortunately we don't get to do that now. And I'm glad that I'm doing this in this video, because this is a little bit more different than what we were just going to be doing, and the next one especially. Okay, so now we just need to write it down over here. So we're going to have 1 divided by root x minus 3 with respect to x. Great. Now that I've dealt with the function over here, we know what we have to deal with. We can just start answering the question, okay? Now from here, well, this is a very much a u substitution question, so we're going to actually let u be equal to whatever's inside the root of the denominator, which is going to be x minus 3. And note that this, when we take the derivative, we're just going to have 1 dx, which can just be written as dx. Okay. Great. And now what we can just do is just substitute, right? But do you remember about definite integrals? With definite integrals, we have to find an upper limit and a lower limit of u. In our case, we're dealing with u. But in this one, we actually don't have to do it. And do you want to know why? The only reason why we actually find, the only reason that we find a new upper and lower limit for u is because we are going to be evaluating with our function, or our integrated function, in terms of u. But we don't always have to do that. So just follow along in this example and you'll see why you don't actually have to find this. So we're not going to do this because it makes a little bit harder. Then we have to basically say like t minus 3 in our bottom. Like we have to say t minus 3 or something in our new integral. That's going to be very complex. Let's make this easier for ourselves. We're not going to challenge ourselves unnecessarily. Okay. So we're going to keep this the same. We are allowed to keep it the same. This is going to be from t to 6. And then this is going to be 1 divided by root of u, because u is equal to x minus 3. That's what we replace with. And dx is just equal to du. So we can replace that as well. Perfect. Now we can integrate with respect to the u, okay? We're not integrating with the definite integral yet, but because that's where we evaluate. This is only the evaluation, not the integral, not the integration. The integration is just when we look at the integral alone with respect to whatever variable, which in this case it's u. So this could be the limit as t approaches 3 from the right hand side, and then we're gonna just integrate. We could have actually written this, by the way, as we know that this could be written as 1 over root u. Or no, 1 over root u could also be written as u to the power of negative a half. And in our case, if we're trying to find the integral with respect to u, then therefore we can say this is going to be u to the power of negative 1 over 2 plus 1 divided by, what is negative 1 over 2 plus 1? That's just going to be equal to a half. And then this is divided by a half as well. And what can we say? This is then going to be simplified as 2 multiplied by u to the power of a half. But we know that to the power of a half means the root of whatever variable. Okay, so that's what we're going to have. So therefore, in this bracket, we're going to have 2 root u, evaluated at 6 to t. And what do we notice? This is x is equal to t, and x is equal to 6, because we haven't found our new limits, right? And we can't evaluate because we have u. But what do we remember u is equal to? We can now plug in our u with, we can replace our u with whatever we made it equal to, which is x minus 3. Isn't that amazing? It's basically about the theory. You need to understand what you're doing, basically. That's what I'm trying to imply over here. You need to understand why you can't do something, why you can do something. Otherwise, you're just waffling, which is sometimes the most common thing in mathematics. But yeah, we're going to have x minus 3, replacing u with x minus 3, okay? And now what can you see over here? Now we can actually evaluate, because we have x now. Great. Now from here, we can just say it's the limit as t approaches 3 from the right hand side. We're going to have our bracket. Then over here, I'm gonna do it in black anyway. The first one's going to be with the upper limit, and then the second one's with the lower limit. So it's going to be 2 into root 6 minus 3, which is with the upper limit. Now it's going to be minus the one with the lower limit, which is 2 multiplied by t minus 3. Okay, because we just plugged in t. Nothing too crazy. And we can actually just simplify this a bit more inside. So we're going to have the limit as t approaches 3 from the right hand side of, it's going to be 2 into root 3 minus 2 into root t minus 3. Okay, now we can just take the limit inside both these terms. But what do you notice? This is a constant. And a limit of anything with a constant is just, the constant is just going to stay the same. Okay. That's what I'm trying to say. So we're only going to take the limit into this, basically. It's really just going to affect the one with the t, because you can see it has t over here. So therefore it'll be 2 root 3 minus the limit, or let's just take the 2 out as well. So we can also take out this constant here, because it can get out of the way. 2 multiplied by the limit as t approaches 3 from the right hand side of the root of t minus 3. And then therefore what we can do, we can take the limit inside to the t, and then therefore we can see that if we do that, we're going to have 2 root 3 minus 2 into, that's going to be 3 from the right hand side minus 3. And then we know over here that 3 from the right hand side minus 3, this will be 2 root 3 minus 2 into, this will be equal to 0 from the right hand side. Because we know 3 minus 3 is equal to 0, right? But if we just add that positive side, then this will also be from the positive side. Because what we are saying is that this is just 3, comma 0, 0, 0, 0, dot, 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 until 1, plus, minus 3. And if we just say that, we're basically just going to minus the 3 over here from the unit, and then we're going to get 0, comma 0, 0, 0, 0, da, 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 1. And that is basically 0 from the right-hand side. Okay, that's exactly what we have here. And over here, well, we're going to already see the answer. The square root of 0 from the right-hand side is just equal to 0. It's self-explanatory. It's so close to 0, and it's just basically going to be rounded to 0. So therefore, that's 0, and 0 multiplied by 2 is also 0. So therefore, this whole thing is going to be out. And therefore, we are left with 2 root 3. And then to end off with this one, is this divergent or convergent? Well, because it's a definite answer and not infinity, we know that this is convergent or converging. Okay. Let's move on to the last example. Here's the final question. Now this looks very interesting, eh? It looks interesting. Here's something new. We're working with negative infinity this time, okay? We haven't worked with negative infinity yet, but it's nothing too different. It's basically the same thing, okay? So once again, we're used to this by now. We're going to take this as the limit as t approaches negative infinity, the integral from t to 0, okay? Like that. And this is of x multiplied by e to the x with respect to x. Okay. Now, because we have a product of two functions, I mean, we would normally be tempted to use integration by parts, which we are going to do. So it's going to work out. We're going to let u be equal. Well, we're going to do, first of all, let's see, what form are we going to be doing it in? We're going to be doing it in the form of from a to b. I'm going to write this down, of u with respect to v is equal to, and then we're going to have evaluated u times v from a to b. minus the integral from a to b of v with respect to u. Okay, so that's what we're going to have. That means we need to determine u and dv, what we're going to be using for u and dv. So we're going to let u be equal to x and dv be equal to e to the x with respect to x, because e to the x is so easy to integrate. It's literally just e to the x. So, and also the differentiation, if you differentiate x with respect to x, it's going to be equal to 1. So that's exactly what we're going to do. du is going to be equal to 1 with respect to x, or it's just be equal to dx. Okay, now with dv, we're going to let this be equal to e to the x with respect to x. So it's e to the x with respect to x, and then obviously in order for us to get it from dv to v, we need to integrate both sides. Therefore, it's going to be v is equal to e to the x. Okay, beautiful. Now what we can do, we can just plug in our stuff over here. But once again, we're only going to be dealing with this integral here. So not this limit over here. This limit is outside the integral. It's multiplying by the integral. So which means we're going to take the limit over here. We're going to have the limit. Let me do it here rather. The limit. What am I doing? The limit as t approaches negative infinity. And then bracket. Big bracket. Should be a bigger bracket. And then it's going to be, now we're going to have u times v evaluated. So it's going to be u. What is u equal to? U is equal to x. And then v is equal to e to the x, right? And this is evaluated from t to 0. Minus, it's going to be the integral from t to 0. And it's going to be v with respect to u. So it's going to be e to the x. With respect to u, it's equal to with respect to x. Okay. There we go. Now that we have that, well, now we can actually go further as to integrate this over here. Okay. So we're going to say this is equal to the limit as t approaches negative infinity of, and then we're going to have, well, it's the same thing over here, x times e to the x evaluated from t to 0, and then we're going to have minus the integral of e to the x is literally just e to the x, so we're just going to have e to the x evaluated from t to 0. And therefore we can actually clean it up also by writing it like this. Because they're both evaluated from t to 0, and here as well, we can actually just write into one bracket. So it'll be the limit as t approaches negative infinity of, it's going to be, let's just do it like this. It's going to be x times e to the x minus e to the x evaluated from t to 0. Okay, great. That's pretty cool. And now from here, well, it would be most prominent to actually just take the upper and lower limits in, respectively. So we're going to have this equal to the limit as t approaches negative infinity of, we're going to deal with, okay, so let's just color code them again. So red is going to be the upper limit, and then blue is going to be the lower limit. So let's deal with the red. So this is actually going to be 0 multiplied by e to the power of 0 minus e to the power of 0. Okay? And this is going to be minus. We know it's minus. And it's going to be, what is t? It's going to be t multiplied by e to the t minus e to the t. Right? So that's what we have. And then we close this bracket. Now we've evaluated both of them. Okay. So our next step is basically just clean it up over here. We can basically just deal with this here. We're going to have the limit as t approaches negative infinity of 0 multiplied by e to the 0. It's just going to be 0. Let me just keep this in red. It's still going to be 0 minus e to the 0 is just equal to, anything to the power of 0 is just equal to 1. So it's 0 minus 1, which we can just write as a negative 1. Okay. And then we're going to have minus, and we're going to have t in blue. We're going to have t multiplied by e raised to the power of t minus e to the t. Okay. And now we can take our limit in. Okay. So once we take our limit in over here, well, we can take it in over here to the negative 1, to the t times e to the t, and we can also take it to the e to the t as well. Okay. But obviously with the negative 1, because it's a constant, it doesn't affect the constant. So therefore, we're really just taking it into the other two. So therefore this is going to be equal to, now I can just keep it to one color. Okay. And then this is going to be, oh wait, no, sorry. It's supposed to be -1 minus the limit as t approaches -infinity of t multiplied by e to the t. And this is going to be minus the limit as t approaches -infinity of, it's going to be e to the t, right? So which one's the easiest one to do first? Clearly this is the easiest one, so let's quickly evaluate that one. So we're going to have -1 minus the limit as t approaches -infinity of t multiplied by e to the t minus, if we take this -infinity in, we're actually going to have something along the lines of e to the power of -infinity, which we can also write as follows, right? So I'm going to do it over here. We're going to have e to the power of -infinity, which is equal to 1. We can also write it as 1 over e to the infinity. And then obviously this will just be equal to, because the denominator is so large, it's basically just approaching 0. Okay. It approximates to 0. Because that's what happens if you take the limit as x approaches, or t approaches -infinity of e to the power of t. So therefore this is just going to be 0, sorry. Okay, now that you've taken all of that in, we can basically do the following, right? I'm not going to get rid of it. I'm not going to get rid of this. I'm just going to basically rewrite this now. It's -1 minus the limit as t approaches -infinity of t multiplied by e to the t. Okay. Now this is where it gets a little bit tricky over here. This is the manipulation with L'Hopital's rule, okay? Because we're dealing with limits, we would most probably use L'Hopital's rule. Now, what happens if we just immediately evaluate, right? Let's just say that we take this over here, right? And then we say it's going to be -infinity multiplied by, let's say it's e to the -infinity, which we know this is going to be equal to -infinity multiplied by 1 over e to the infinity, which is just going to be equal to -infinity multiplied by 0. This is an indeterminate form. So therefore we should use L'Hopital. Now how are we going to be using L'Hopital though? That is the question. The reason why I'm saying that is because, sorry about that, is because we don't have a quotient. But we are going to make it a quotient, okay? Against its will. We are going to force it to become a quotient so that we can actually answer this question, because it's being a big problem right now. So we have the limit as t approaches -infinity. And how are we going to manipulate it? Now I'm going to do it in 2 different colors, and you're going to tell me which one is correct. Or we're going to do it like this, because we can also write this expression like this. E to the power of t divided by t to the -1. Because it's the reciprocal of this divided by that. And it's the same thing. Or are we going to write it like this? Are we going to write it like this? T divided by e to the power of -t. Which one is better? Now I want you to actually try these two yourself to see which one is better. Okay, so you can pause the video, you can try and see which one are we going to use. Okay. You done? Great stuff. So we're not going to be using this one. And the reason why is because it's going to constantly be indeterminate. This denominator, if you're differentiating it, it's going to keep going up, like t to the power of -2, then t to the power of -3 if you keep differentiating it. And that's going to be a huge problem. Okay, it's still going to be indeterminate form. So that's why we're not really going to be using it if you picked it up when you were practicing. So therefore we're going to be using this one. Okay. So let me rewrite it here, just for the sake of the video. -1 minus the limit as t approaches -infinity of t over e to the power of -t. Okay. Now let's deal with this. Okay. We're going to deal with this over here. So over here we're going to use L'Hopital's rule on this one. If you already did it, you already see that it will give you a nice answer. If we're differentiating over here, we're going to differentiate the numerator, and therefore, so we're going to get the limit as t approaches -infinity, and then we differentiate the numerator, that will be t, differentiated will give us 1, divided by, and then differentiate e to the power of -t, it's just going to be -e to the power of -t. Okay. Now, what do you see? This is actually perfect. So now what we can do is we can actually just take this negative out so that it basically gets rid of our problem. So it'll be negative limit as t approaches negative infinity of 1 over e to the t, negative t. Okay. Which we can actually just write as e to the t, because that's the reciprocal. So let's plug this into that, okay, with what we have in the red. So therefore it's going to be equal to 1 minus, we're going to have minus negative limit t approaching negative infinity of e to the t. Okay, so that's what we have. And what do we notice here? The negatives will multiply each other such that they cancel. This will be negative 1 plus the limit as t approaches infinity, negative infinity, sorry, of e to the t. We can just write this as e to the power of negative infinity, and then therefore we can actually write this as negative 1 plus 1 over e to the positive infinity, and therefore this, we know that this is going to be equal to 0. So this is negative 1 plus 0, where the answer will be equal to negative 1. And then just to end off over here, is this divergent or convergent? Because it is a definite answer, the answer would be convergent.